So far in this course we have seen the NMOS depletion enhancement mode field effect transistor, and how we came up with it was the following. Let me give you a quick reminder. We said we are going to have a passive 3-terminal 2-port, this is terminal 1, this is terminal 2, and this is the common terminal. And we basically said that if the device has to have gain, then it has to be nonlinear, and the incremental y11 and the incremental y12 must be 0, and incremental y21 must be as large as possible, and incremental y22 must be 0. Y12 must be 0 to avoid problems with stability. And a possible set of characteristics that satisfy these constraints is that port 1 current is 0. Okay, remember that port 1 current need not be 0, all that it needs to be is to be a constant, right. If that constant is 0, it is a special case, and it turns out that in practice there is devices which do this. And of course I2 is only a function of V1, right. So this is capital V2, this is I2, and this is capital I1, and this is V1. Okay. And we also recognize that this is not possible for all. The port 2 current cannot be only a function of port 1 voltage for all values of V2, right. For as V2 becomes sufficiently small, we basically end up with the characteristics, the output characteristics have to eventually become will not be parallel to the x-axis. And so the characteristics we got, assuming that the device is passive, is basically we got I2 versus V2. If you plot there is nothing to plot as far as the input characteristics are concerned, because I1 is identically 0. For the output characteristics, we saw a family of curves like this, which do right. And we said that, well, in our discussion on which eventually led to the NMOS transistor, we said I2 is positive, V2 is positive, because the characteristic, the output characteristic, given passivity and the fact that capital I1 is 0, can only be in the first or the third quadrant, right. So the first quadrant behavior basically led to the NMOS transistor, right. So it's, and because you can have something in the third quadrant, it is not surprising that you can also find electronic devices which basically have a characteristic which is in the third quadrant. So basically you have something like this. Okay, and so in this case, therefore V2 is negative and I2 is negative, I1 is 0, all right. And so therefore if V2 is negative and I2 is negative, I1 is 0 anyway, so that goes away. So it turns out if I2 is negative, we basically change the direction of the arrow, and V2 is negative, so we basically use right that as V2, right. So that this way the V2 and I2 can be, I mean, if you compare it with our NMOS, the earlier 2-port, I mean it's just that V2 and I2 are reversed in sign, The only, I mean, and the reason to do that is that otherwise you have to turn your head, 180 degrees and look at the graph. Okay. Now, because we have denoted V2 and I2 as shown here, okay, we might as well also call this V1. Okay. So, what comment can you make now? What if you denote the difference between the common terminal and the terminal on top as V2, what comment can we make about the characteristics? They all shift to the first quadrant. So, this is just nothing but mere what you call notation gimmickry, just to make our lives easier, right? And so, therefore, we are back to square one. So, the characteristics also look like this now, and we are often we live in a gravitational field where the potential at a point higher is lower than a potential which is physically lower, right. So, it seems a little bit awkward to say that in this picture, in this diagram that we see here, it seems a little bit awkward that the higher potential point is physically at a lower point, whereas a lower potential point is is higher, and also seems kind of a little unnerving that current flows against gravity, right, though gravity and current have nothing to do with each other, right. There is nothing wrong with pushing the current up and then having the current always flows from a higher potential to a lower potential. So, there is nothing wrong. The lower potential is below and then the higher potential is above, I mean the higher potential is below and the lower potential is above, and it, therefore, I2 flows from down to up, right. But this is it's kind of a little bit unnerving for us, having been used to fluids flowing down and everything flowing down because of the way gravity is, right. So, rather than I mean the only way to fix this diagram, there are only two ways of doing it, right. One way is to stand with your head on the floor, and then everything will appear natural again, because the lower potential will be again lower and the higher potential will be higher on the paper, right. And of course, that does not seem like a very practical thing to do. So, what do? Well, you turn the book around, right, which also seems not quite practical. So, you might as well say, well, you turn the diagram around, right. So, basically what you do therefore is you draw the diagram this way, all right, and this again now becomes capital V2, this is capital I2, okay, and this is capital I1, which is 0 anyway, and this is what we call V1. All right, and what do we call? I mean, now based on our experience with NMOS transistors, which terminal will we call the source? What was the source when we talked about NMOS devices? What was the common terminal was called the source. So, that is still the case, all right, and which is the gate and which is the drain? This is the gate and this is the drain. All right, and again the drain current is independent of the drain source voltage or the source drain voltage. Remember, which is now at a higher potential? The source is at the highest potential, the drain is at a potential lower. So, as long as the source drain potential is sufficiently positive, so okay, so this V2 is also the potential between the source and the drain. The source must be at a higher potential, and this is of course the drain current, and we can say that the drain current is independent of the source drain voltage as long as the VSD is greater than some V minimum. Okay, so VSD must be greater than V minimum for ID to be independent of Vs. All right. So, okay, and in the NMOS case, this statement would be VDS must be greater than a minimum voltage for ID to be independent of VDS. Okay, and the equations, surprise, surprise, are also very similar. So, what is the, now you know the orientation, now it should be straightforward to write the equation. So, ID turns out to be, again, first of all, if VSG, right, is less than some threshold quantity called VT. And now, earlier for the, now we have two kinds of devices. Those are called the earlier devices were called the NMOS transistors, and their threshold was VT. Now, since we have a PMOS transistor, this is what is called the PMOS transistor, and therefore, to distinguish the thresholds of the two devices, now you have a new subscript. So, VTP represents threshold voltage of a PMOS device, whereas VTN denotes the threshold of an NMOS device. So, if VSG is less than VTP, okay, the transistor is off. Okay, all right, and by the way, the how we draw the symbol is also very similar. For the NMOS transistor, what did we do? What was the, the gate, the source and drain are that's straightforward, right? Source, gate, drain. Okay. Now, in the NMOS case, where was the arrow? In which terminal was the arrow put? In the source. So, here also we should put it in the source. Now, what did the direction of the arrow indicate there? Direction of current. So, here which direction does the current flow? Flows into the source. So, basically, if we use the same logic, then this must be the symbol of the PMOS transistor. Correct? So, if VGS is less than G, S and B, if VGS is less than VTP, the device is off. Okay. If VSG is greater than VTP, all right, then the current is independent of the drain source voltage or source drain voltage, and is only dependent on the source gate voltage. So, VSG minus VTP the whole square. This is provided VSD is greater than VSG minus VTP. VTP here is also a positive quantity, right, again corresponding to what is called an enhancement mode. PMOS transistor. Okay. Now, in English, what does this mean? In the NMOS case, what did it mean for a transistor to be, what is the minimum voltage needed for the transistor to remain in saturation? Yeah, so basically VDS had to be greater than VGS minus VTN in the case of an NMOS transistor. In the case of a PMOS transistor, do we want the drain potential to be as low as possible or as high as possible in the PMOS case? We want the drain potential to be as low as possible so that VSD becomes very large to maintain the transistor in saturation. Okay. So, I mean, a lot of people get confused about this VSG, VGS and all this stuff, which is positive, which is negative and all that. The easy way to remember it is basically to recognize one basic fact, and that is that current always flows from a higher potential to a lower potential. So, if you start bringing the drain potential closer and closer and closer to the source potential, there is no potential difference, right, or you bringing the potential difference closer and closer to 0, and therefore current cannot flow, right. Okay. The more the difference is, I mean, the easier the current is to flow. So, and in the transistor, basically, if the source drain potential, I mean, if the potential between the two terminals, drain and source, is very large, okay, and is in the right direction as far as the symbol in the arrow is indicating, right. For example, in the PMOS case, the arrow, the current must flow into the source. So, yeah, you conclude that the source potential must be much higher than the drain potential if you want to maintain the transistor in saturation. If you look at an NMOS transistor, the current flows out of the source. So, the drain potential must be much larger than the source potential to maintain saturation. So, do not get confused between, if you get confused with regard to the formulas, right, always use, physical intuition, right. Current always flows from a higher potential to a lower potential, right. And therefore, in a PMOS transistor, the transistor will trend to get into the triode region, which is the beginning of where the current flow begins to drop, right. So, the current in the drain was, when the drain was at a very low potential, there was some current, which is constant. As you keep increasing the drain potential, the potential between the source and drain starts to become lesser and lesser, and therefore, it becomes more and more difficult to maintain current flow, right. Okay. And therefore, so as the drain potential keeps going higher and higher is when you have a problem in the PMOS case, all right. So, in English, therefore, what does this sentence mean? VSD must be greater than VSG minus VTP. That means that the edge of the triode region is defined by the drain potential going, basically the drain, this is the easy way to remember it, the drain can go 1 VTP above the gate. Right. In the NMOS transistor, what was this? The drain can go 1 VTN below the gate, all right. Okay. That is I find it personally much easier to work with that than to sit and do this formula stuff, which is basically the same thing, correct. So, in a PMOS transistor, the drain can go one threshold above the gate before the transistor gets into the triode region. In the NMOS transistor, the drain can go one threshold below the gate, and that will be defines the edge of or the boundary between the saturation and the triode regions. Is that clear? All right. And of course, now what happens if the drain indeed goes higher than one threshold above the gate, well, the form of the equation is really the same. It's mu p Cox. The transistor gets into the triode region, and in the triode region, what is the equation of the NMOS transistor? In the NMOS transistor, what was the equation? Mu n Cox W by L times VGS minus VTN times VDS minus VDS square by 2. So, now use now tell me what it should be for the PMOS device. Mu p Cox W by L VSG minus VTP times VSD minus half VSD square, and this is provided VSD is less than or equal to VSG minus VTP. So, this is the triode region. All right. Okay. So, drain, source, gate, source, gate, drain. Okay. So, the current flows in this direction, the current flows out of the drain, right. To keep the transistor alive, you want the VGS to be greater than a certain amount. Here you want the VSG to be greater than a certain amount. You want the drain to be, if you want to keep the transistor in saturation in the NMOS case, the drain should be very high compared to the source. In the PMOS case, the drain must be much lower than the source, right. But otherwise, it's pretty much the same. So, whatever you can do with an NMOS transistor, you can also do with a PMOS transistor. All right. So, the obvious question therefore is what then? Yeah, that is a reasonable question, right. So, I mean, if I can do with him what I can do with him, why do I need two people, right? I mean, I just hire one, isn't it, right? So, the question is, if the equations are the same, it must follow that you can pretty much do what you want. If you could do something with NMOS transistors, you could also do it with PMOS devices. So, why do you think, why are we wasting our time studying PMOS transistors if, whatever you can do with NMOS, you can do with PMOS? Why are we studying these devices? After all, I mean, you must have, have you studied MOS devices in MOS circuits in your undergraduate, or is it bipolar? Bipolar, right? Bipolar also has got the same thing, right? You have NPN, PNP. Characteristics look similar, equations look similar, everything is pretty much the same, only some directions of current and voltage change. So, why bother? Why are we, why are we studying two kinds of devices? More importantly, why are we making them, right? Evidently, making another kind of device needs more effort, right? So, so why do we need both of them? Complementary behavior, right? So, basically what, and when you say complementary behavior, it basically means that you can do something with this guy, you can do the same thing with this guy, but if you put both of them together, you can do things which you cannot do with either one of them alone, right. So, and a classic case in point is the following, right. So, if the potential goes, if the drain potential of an NMOS transistor goes down, right, the NMOS transistor starts getting into the linear region, right, whereas the PMOS transistor is very happy because its source drain voltage is increasing and therefore it is going deeper and deeper into saturation. Another example of complementary behavior is that the NMOS transistor behaves like if you want to make a current mirror, for instance, current is being pulled down in an NMOS device, right. What if you want a current source which pushes current? That is a PMOS transistor, right. So, if the PMOS transistor has got a constant source gate voltage, then the transistor pushes current. So, it can be thought of as a current source, whereas an NMOS transistor is a current sink, all right. So, by combining NMOS and PMOS transistors, right, even though the individual transistors by themselves can only do something which is limited, right. When you combine these transistors is when you get a whole new range of possibilities that are enabled by complementary behavior, right. One of the biggest advantages, as he pointed out, is in digital logic circuits, not because you cannot get logic high and logic low without complementary transistors, right, but the fact that you can make both logic states in such a way that there is no power dissipation is what is key, all right. We will take a look at that, going forward. Going forward, we will, after going through the basics of repeat everything that we saw with NMOS, with PMOS, just for sake of completeness. We will then see how we can combine NMOS and PMOS transistors together to do things which were not possible with either kind of devices, right. So, that is why we are studying PMOS devices. Okay.